Hello, I'm Ruth Britto, and I'm happy to have this chance to introduce a bit of the research happening in theoretical physics at Trinity. There are many angles from which physicists approach fundamental questions such as what is everything in the universe made of? How did it come about? What other universes are possible? And what are the reasons that we find ourselves in this one? This short presentation deals with the question of what the fundamental constituents of matter are, how they interact, and more specifically, the question of how we can figure that out. Here are the particles that have been unified into the standard model of particle physics. They are the elementary components of matter and carriers of the fundamental forces. The only one that's not pictured here is the force carrier for gravity. The unification with gravity with the other forces is actually related to my story, but I won't be able to get into that in this short talk. The theory of how these particles relate to each other was mostly complete by the 1970s, but the actual discovery of the last ones, not to mention the measurement of their parameters, has taken a great deal of time and energy since then and is still ongoing. There are many basic questions in physics that lead us to want to understand in great detail whether this picture is really truly correct and how there could be room for anything else, because there are reasons to believe that it's not complete. For example, one famous question of this type is, what is dark matter? Another is, could there exist extra dimensions of space at short distances? Of course, some of these questions are related to the problem of unifying gravity with the other forces. There are several avenues for seeking answers to these questions and several types of experiments, but one clear and popular avenue is with the method of setting up high energy particle collisions in accelerators. The major experiments of our time take place at the Large Hadron Collider, called the LHC, at CERN in Geneva. The LHC announced the discovery of the Higgs boson in 2012, which was the last outstanding element of that chart, and one that has really unique properties. The accelerator is planned to continue operating until at least 2036, and the experiments there will be studying the precise properties of that Higgs boson while continuing to search for other particles and phenomena. Now, particle accelerators in principle are possible in no small part due to the work of our own Ernest Walton, a Trinity undergraduate and professor who won the Nobel Prize in 1951 for his achievements in nuclear physics. The LHC is colliding proton beams. Proton collisions are very messy because protons are not fundamental particles. They're composed of several of the other particles that we saw at the start, specifically quarks, which are being held together by gluons, the carriers of the strong force. So there are quarks coming into the collision point and quarks coming out, but quarks can't survive on their own, so they assemble into other particles in turn that can then be observed in the detectors. There's really a lot going on. In the very middle of this, there's what we call the hard scattering, which is where something like the Higgs might be produced and then immediately decay into other particles because it simply cannot survive for longer than the briefest instant. In this diagram, now a cartoon, the hard scattering is hiding inside the blue blob in the middle, which indicates that we have no direct access to that information in the experiment. And there are other things that could possibly happen inside that blob that do not involve the Higgs, say, if that's what you're looking for, but with exactly the same types of initial particles and final particles. So the only way to know that there's been something new that happened inside is to do a lot of calculations and run the statistics. Here's one of the plots from the Higgs discovery. The Higgs shows up as this little bump on top of a smoother curve of all the non-Higgs scattering. So we need to do a whole lot of precise, detailed calculations to be sure that we're making the right predictions. This becomes even more important as we study the Higgs in more detail, and especially as we continue to hunt for particles and phenomena that are much more speculative. Now I'd like to invite you to look closely into that blue blob. What's in there and how do we calculate it? If you come and take quantum field theory in your 4th year, you'll learn that when particles are moving at or near the speed of light, as these protons are, then we set up something called a path integral to work it out based on the information about the particles going in and coming out. But you'll also learn that there's a beautiful and simpler way to calculate, which is by the method of Feynman diagrams. In brief, We draw pictures of all possible ways that we can interpret this interaction point as being mediated by all the various particles. Well, not all possible ways, because as you might expect, there are infinitely many of them as you put in more and more intermediate particles. But you can make increasingly good approximations as you increase the number of closed loops that are allowed in the diagram, starting from 0. And that's what we do. Then we have rules telling us how to go from the pictures to algebraic formulas. And what's missing from this cartoon diagram is that you would have different kinds of lines indicating what types of particles are really involved in each of these interactions. Now, this technique of Feynman diagrams and Feynman rules is really great. In fact, Edward Tufte, a man who's known for his work on infographics, has called Feynman diagrams the best visualization ever, because they're simple to look at, they make calculations simpler to do, and they express a deep truth. Edward Tufte has made art installations with Feynman diagrams that are formed from stainless steel. One of these installations is this one, which depicts the scattering of 6 photons. Photons are light particles, also known as the carriers of the electromagnetic force. So this is not directly relevant for the LHC, but the idea is the same. This small image shows the scale with a person. So they're not huge, you're meant to see all of them at once. But I'm also showing the diagram somewhat larger here, so that if you look closely, you'll see that there's just essentially one diagram that's being twisted in different ways. And that reflects what we do in the physics. Sure enough, we do essentially have just one expression to compute, but to get the answer right, you then have to interpret it in different ways because you have 6 different photons, and then you add them all up. Now that part isn't hard to generate all the different diagrams once you have one of them. The hard part is computing any single one of those diagrams. Because it turns out that although Feynman diagrams are truly very helpful, only the simplest ones are easy enough to compute by hand in your 4th year coursework. The one here is quite hard because there's an electron going around the loop and because there are 6 particles involved on the outside. So for the work being done in the LHC era, we need not only powerful computers, but also powerful new ideas. In fact, we do have some good ideas, and that's my research topic in brief. Let me just leave you with this hint of what's going on. When you work out the sum of all the Feynman diagrams that you need, like the sum of these 120 photon diagrams, you find a result that's far simpler than what you get from any individual diagram. In other words, there are some secret cancellations that are hidden in the usual method. The work we're doing now is to understand what these cancellations are, and more importantly, why they're happening. The idea is to then get to a radically different understanding of the fundamental interactions, one that will let us get to the simple parts straight away. This research has already helped in the theoretical effort supporting the work at the LHC, and it paves the way for future predictions and experiments in particle physics. So in sum, I believe there should be something even better than Feynman diagrams coming up, a deeper version of the truth of fundamental interactions. Will you help to discover it? Thank you for watching, and best wishes to you all.